So for everybody who hasn't been here before, hello, welcome to the BS and Beer Show. BS stands for Building Science. I am Emily Mottram. I'm an architect here in Maine. Tonight I'm actually drinking black cherry seltzer. Probably good if I'm in charge tonight if I don't drink. Just kidding. BS and Beer is a grassroots independent movement where everyone here is volunteering their time to bring building science to you. So thank you to all of our guests and everybody who shows up in our audience for their time that they come and share with you. We want to thank Green Building Advisor and Fine Home Building. They are our media partners that make this happen every week live on Zoom on Thursdays and post it up on the YouTube channel and the Green Building Advisor blog, where you can continue the conversation after the show if your questions don't get answered. Post your questions in the chat box. If you are new to Zoom, the chat box is on the bottom and it's probably flashing because everybody is introducing themselves. We would love it if you introduce yourself and what you're drinking in the chat box. Make sure you pick all panelists and all attendees. Otherwise, your fellow guests can't see that you're here. So if you want to have fun conversations with your friends in the chat box, all panelists and all attendees. Otherwise, it only comes to the panelists and they can't see what you're sharing. Fine Home Building sends out a Zoom reminder every week. That's just a reminder for the link for the live show. If you'd like to know what the next show is going to be and to read the bios for our upcoming guests, pop over to the bsandbeershow.com and join our mailing list where you'll get updates and sometimes questionnaires on what you'd like to see or hear for us on the show. The video recording for tonight's show will be available on our YouTube channel and through the Green Building Advisor blog post. Again, we encourage you to continue the conversation there if you didn't get your questions answered. We have a couple of special announcements. The first one is we are writing the Pretty Good House book. And the Pretty Good House book is looking for case studies. So I'm going to post a link in the chat box for people to submit their case studies. If you'd like to see your case study happen in the book, if you think you've if you think you've built or have designed a pretty good house, feel free. We want to make sure we cover all of the geographic regions. So go ahead and submit those. The call for entry will be in there. I'm also going to add links that we post every week for Skills USA and a couple of other podcasts and associated crossover shows that we are proud to have also providing building science knowledge. So with that, Ben, if you want to introduce yourself and our guests.
All right. Thank you, Emily. So I'm Ben Bogey, your favorite bearded weirdo, working as a project manager in Connecticut. This evening, I'm drinking a Mason's Liquid Rapture. This is my second attempt at a beer. The first one I cracked when I sat down was absolutely atrocious, so I had to go for this, my backup beer, and it's much better than the first. So this evening, I'm really thrilled for this panel tonight. It's four people that I have a tremendous amount of respect for and can quickly, in a matter of seconds, start talking about things that blow right over my head. So I'm looking forward to learning a lot this evening. First off, I'd like to introduce John Loecher. John is a consultant on energy modeling and envelope design. His firm, Northeast Projects, specializes in passive house design and certification. Their projects include single-family, multifamily, commercial, new construction, and retrofits. John and I had the pleasure of working on a project together a number of years ago, but like two ships in the night, never managed to cross paths. So John, if you'd like to tell us what you're drinking and anything that I missed there, please feel free.
Sure. Cool. Yeah. Thanks for having me. And nice to see you, Ben. We managed to work on that project together. And like you said, just never, ever even see each other in person. I am drinking a Yes Folk kombucha from Troy, New York, a little microbrew kombucha, because I still have to put my daughter to bed after this. So the beer will wait until later. Yeah.
Excellent. Thank you, John. Next up, Ed May is an architect, passive house consultant, and educator. He teaches with Passive House Academy, the North American Passive House Network, and Passive House Canada. Ed, pleasure to have you this evening. What are you drinking?
Well, we happen to have an awesome Japanese grocery store in the ground floor of our building. So I have a Sapporo Black tall boy for tonight's festivities.
Minus the brown paper bag.
For the time being.
Thank you, Ed. Pleasure to have you. Next up, Allison Bailes earned his semi-famous status from his Energy Vanguard blog, which is phenomenal. If you don't follow it, you should. His company does third-party residential HVAC design for clients across North America. Allison, how are you this evening?
I'm doing great. I'm glad to be here, and this is going to be a fun topic. We do a lot of load calculations at my company. I don't do them myself so much anymore, but I'm still involved in everything. And I am drinking And We Pray from Burial Brewing in Asheville, North Carolina. It is a rustic saison.
Nice. Sounds delightful. And finally, Marc Rosenbaum is an engineer whose recent work has been zero net energy buildings, deep energy retrofits, and passive house projects. His work has been recognized nationally by various groups, but they didn't see all the mistakes along the way. He's made more of them than you have. Mr. Rosenbaum, pleasure to have you this evening, sir. What are you drinking?
So first of all, I have a very low tolerance for alcohol. My wife is of Irish extraction at half my size, and I have never seen her tipsy. That is not the case for me. I am drinking Mayflower Porter, and I have cut it 50-50 with Newman's Lemonade to make what is called a shandy, which I learned about when I hiked the Pennine Way in 1977. It was the only way I could begin to keep up in the pubs with my English hiking companions.
I think it is officially shandy season, so good form, sir. So I believe everybody has a presentation that they'd like to go through this evening, at least a few slides. Does anybody want to volunteer to go first?
Oh, were we supposed to have a presentation? What?
I think so. Okay, Mark's waving his hand.
I think I was supposed to go first. And I would like to do that because I have less real information than the other ones that are going to follow me. So I'm going to try
to yours, sir.
I'm going to try the share screen thing and see how that goes. Okay, can people see this?
Excellent. We've got you clear.
Yes.
All right, great. So one of my favorite quotes there: "All models are wrong, but some are useful." And you know, what I'm showing here on the cover page is nothing that anyone will not be on the quiz, but it's really to illustrate the fact that models are just a series of calculations, and they don't have to come out of a piece of software. It doesn't have to be Woofy Passive or Energy Plus or whatever. You can make your own model. And so you're seeing a model in the lower right-hand corner of embodied carbon of a house, and then you're seeing forecasted both electrical and thermal loads in the lower left-hand corner for a whole farm that has a 30,000 square foot Dutch greenhouse. Upper right-hand corner, you're seeing sort of a hand calculation of daylight modeling for a university building. And then on the upper left, you're seeing the output of actually a really sophisticated multi-page Excel model that looks at hourly data and inputs to model off-grid buildings. And looking at generators and grid emissions and batteries and optimizing for lower emissions than the grid, which is actually difficult to do when you're off-grid. So that's my point, is that models are just calculations, and they're only as good as what you put in them and how you build them. There we go, good. So I have three examples of, I've probably reviewed more load calculations and energy models than anyone else attending tonight, because I've worked at many different building scales, and oftentimes I'm a performance consultant and I'm not the engineer on the job, particularly in larger buildings. So I've looked at many people's energy models for particularly larger buildings and a lot of load calculations. So this is a fairly recent project, maybe 3 years old. It's a giant, it's not a passive house certified, but it could easily be a passive house. It's in the Boston area, and it was design build. I did the mechanical concepts, but there was also a mechanical contractor on the job. And let's see how I make this work. That was the first manual J that I got. Now, I don't do manual J. I have my own spreadsheet for heat loss. 90,000 BTUs an hour. And that was from the HVAC sub. And I sent them back and said, no. They had a proposal for a mechanical system that was 11 tons of heat pump on this project. And so I said, you need people who really can do manual J and specialize in that. So they brought back someone else who was close, only 2,000 BTUs an hour less. I said, let's try one more time. And we got 101,000. So, you know, at least we have consistency. That's my heat loss. This building's built. It's designed to that heat loss. And it's been lived in some fairly severe weather, and it's got plenty of capacity. So what's happened in this first three? The biggest error is overestimating infiltration, really overestimating infiltration. And so the consequence would be a vastly oversized system that would work really badly compared to a right-sized system. The second case is a deep energy retrofit in Western Mass. It started as a nondescript warehouse attached to a 3-story masonry bearing wall building, all masonry, all pretty much uninsulated. And you're looking at, again, 3 heat loss calculations: the HVAC sub, the construction manager who's really into this stuff, so he did 1 too, and then the third column on the right is mine. And you can see here again the difference in the calculated heat loss for this building. And there's some differences in infiltration, like with the HVAC sub. The HVAC sub and the CM are not accounting for the energy recovery. So the ventilation load is the same in terms of CFM, but they're not accounting for the fact that there's an energy recovery ventilator for this building. And then the big difference is heat loss through the slab. So many CAN programs do a really bad job of heat loss down. And I think that actually extends to the passive house software. That's why we've ended up with so many buildings with 12 inches of foam beneath basement slabs. And Ed and John, you're welcome to argue with me. That'll make it interesting. And once I have enough beer, you'll probably convince me. But once again, look at the difference in the size of the system that would result for this. You know, I'm a really expensive consultant. My watchword for decades has been never use a small word when a large one will do, and you can be billable by syllable. So I'm expensive, but you can see on these jobs that the difference in the mechanical system cost pays for a pretty exorbitant fee. And then this is a building that's still under design. It's going to get built, started this year. It's a lab building in New Hampshire. It's added onto an existing lab building. It's the same company expanding their business. And the mechanical engineer, and this is a PE, and this is actually a good PE. His system concepts are great, very attentive, detailed drawings. His load for this addition, 30,000 square feet, is 323 tons. Now that's a lot. You know, if you want that in kilograms, I'm going to have to do the math in my head. Allison could probably do it, but tons is a lot, and 323 tons is a lot, and 100 square feet per ton is a lot, right? So that's a really big building in terms of its size, but it's a really big building in terms of its load. And I've done buildings that are 200,000 square feet that are less than that, right? The MIT Sloan School of Management is, I think, about 220 tons for over 200,000 square feet measured. So you have an existing building here, and you can look at the load of that building. So I had them get 15-minute electrical data for that building, because this engineer's load is driven by the internal gains. And I said, well, we've got electrical data for the existing building. Let's look at it and see what we think those gains really are. And so we looked at a year or 2 years, I guess, worth of 15-minute data to look for the maximum. And we found it. And then we subtracted the clearly large loads that didn't contribute to a cooling load, like some of the fans, the exhaust fans and stuff. And we end up with a building that has less than 100 tons of load. So how much money did you put in your pocket when you cut 225, 250 tons out of a building project? I mean, this is real money. This is several $100,000. It's probably more than Allison makes in a week. So the point is, even if this isn't your business, getting familiar with what the answer should be is a really powerful strategy for builders, architects, owners to make sure that they're getting accurate loads. And then the last thing I want to talk about is the benefit of mutually canceling errors in building energy models. So this is the Kern Center at Hampshire College. It's a certified living building. And I did the building performance stuff. I wasn't the mechanical engineer of record, but in terms of who's going to call for how much PV this building needs to be net zero, that was my job. And on the right, what you're seeing is the dotted lines are my model and the bars are the actual data. And you can see that I underestimated the heating load. And I'm not sure exactly at this point where that is. I mean, it could be the heat pumps working at a lower COP than I guessed in my model. It's challenging to guess what the actual COP is of a heat recovery air source heat pump system. And you can see that I overestimated the cooling in the summer. So this building ended up within a few percent of what I predicted it would use, but where it actually uses energy is different than what I predicted. And I think, it takes some really good fortune as well as a good model to end up with a model that really conforms exactly with what the building is doing. One of the last thing I want to say about this building, which is interesting, is the building engineer who actually worked at Hampshire and got the building really working well, terrifically skilled guy, Todd Holland, was very disappointed in some of the aspects of how I was off on the individual components. And one of the ones that he called out was that I only estimated that the cafe would use about half of the energy that it uses. And one of the things about making a really great building is that people will use it more than you ever thought. And so there's a lot more people in this building. They come from all over campus to be in this building because it's a great building. And I think it's, we're here tonight geeking out, but it's always really good to keep in the forefront of our minds that what we're trying to do is make great buildings for people and for the planet. And if they use more energy because people are using the buildings more, that means we did a good job. So with that, I'm going to hand it over to people who are more skilled and smarter. And how do I unshare? Just hit the stop share.
Yeah. Got it.
Okay. Thank you.
Thank you, Mark.
Cheers.
Allison, you, sir?
Okay. All right. So we got the MIT presentation there. I've just got a degree from a state school, so I'm going to, I don't know how I'm going to do this, but let me try it. All right. Share screen. Desktop 2. Share. And then presenter view. Okay. Can you see that okay? All right. So I'm going to talk just about load calculations. Mark kind of mixed in a little bit of load calculations and energy modeling. And I believe Ed is going to go after me and talk about energy modeling. So the difference between energy modeling and load calculations is the time scale, basically. Load calculations give you the peak heating and cooling needs for the building so that you can size the mechanical equipment for it, the heating system, the cooling system. Energy modeling is for telling you how much energy that building is going to use over the course of a longer time span, usually a year. And that goes into some programs and certifications and energy modeling numbers like the HERS index. And Passive House has its tools and metrics. But with load calculations, it's all about the peak heating and cooling needs so you can get the mechanical equipment right. So here's how you do it. It's pretty simple. You just, 1 ton of capacity every 500 square feet. Now you may think, okay, well, Mark's sitting there. I'm in Massachusetts. That sounds like it's too much for me. So, okay, in Massachusetts, maybe 600 square feet per ton. Florida, maybe 400 square feet per ton. That's all you need to know. That's your load calculation right there. Well, okay. Now this is how contractors do it, but really you should be using something more sophisticated. Here is manual E for eyeball. I've got this. This is a transparency. You cut out the shapes. You stand 103 feet away from the house, hold it up, and see which one the house fits in better, and that shows you what size equipment you need: 5 ton, 4 ton, 3 ton, or 2 ton. Pretty simple. Okay, again, that's not what you want to do. You want to use here's another one. This one actually is decent. This is called the Mills 220-200 rule, and I just heard about this today from Dan Holohan, who's a steam heat guy in New York City. John Mills was a guy in the 19th century who designed steam heating systems for big buildings, and the 220-200 rule is much more sophisticated than what a lot of contractors use today. The 2 is for the glazing area. You find all the glazing area in the building and you divide it by 2 and you hold on to that number. The 20 is for the cold surfaces. You get the areas of all the floors, walls, ceilings, everything that is between the heated space inside and the unconditioned space outside. You divide that by 20 and then hold on to that. The 200 rule is for the air, because we have heat loss associated with the infiltration. These old buildings in the 19th century especially were quite leaky. So you get the volume of the building, divide by 200. You add those 3 numbers together, and that gives you the square footage of the radiant area that you need to install in that building for, 215 degree steam. So that is actually a pretty sophisticated rule. It doesn't work with modern buildings, but for buildings in the 19th century, it worked. Let's talk about the right way to do it now and I'm talking about houses here, not big buildings, but the same basic procedures apply. This is a diagram straight from Manual J, which is the protocol for doing load calculations that the Air Conditioning Contractors of America has developed. That, as Mark already has told you, it's not the only way to do load calculations, but the basic principles inside each method are the same. You do the heat loss and heat gain through all the different surfaces, add infiltration, internal loads, all that stuff. So here's the diagram showing for heating, the things that you have to account for. Heat loss through all the surfaces: the windows, the doors, the ceilings, the floors, the walls. The any duct losses have to be accounted for if you have ducts outside the conditioned space. Ventilation air has to be heated or when you bring it in, and so all those things have to go into the load calculation. On the cooling side, it is, went too far. Jumped ahead there. On the cooling side, it's almost exactly the same. There are a couple of important differences though. For cooling, you have some loads that Manual J does not count for heating. One is the solar gain through the windows. So when sunshine comes in and heats up the house, you've got to account for that, and that's included in the Manual J load calculation for cooling. And another one is the internal load. So the heat that people give off, the heat that appliances and lights give off, all that goes into the calculation. And then one other big difference is that the cooling load is divided into 2 different kinds of load: sensible and latent. The sensible load is the load associated with changing the temperature, either cooling the air in summer or heating it in winter. And the latent load, well, okay, we're just talking about cooling. So, but in wintertime, there's sensible load as well, and it's only sensible load. The latent load is the load associated with removing water vapor from the air. In a humid climate, that's very important. So you calculate both of those, and that tells you what kind of equipment you need. Now, it's possible to do this wrong. And a lot of people do this wrong. And, they end up with this kind of situation here. This person clearly did not understand load calculations. So if you do it right, you end up with this situation. Now you see this truck's going down the road. They're just fine. Everything's fine. They did their load calculation and it works. So that's it. We'll get into a lot more detail with this in the discussion. Let's see. Oh, stop share. There's the button.
Beautiful visuals, sir. All right, Ed, I believe you're up next, sir.
Sure, absolutely. Can you guys all hear me okay? Fantastic. And hopefully everybody can, excuse me, see my screen all right? All right, fantastic. So first of all, thanks for the invitation. It's a real honor to be here with everybody. Mark and Allison, I've learned so much from you. You didn't know this, but I've learned so much from you guys over the years. So thanks for all that you guys have done, publishing and sharing the information that you've learned over the years. And it's a real honor to be here. And John, of course, you and I go way back as well. So it's awesome to be here with all of you guys. So thanks for the invitation, first of all. So that's all fascinating. I agree with everything that Mark and Allison just said. I think that's super interesting, and those load calculations are incredibly important. What I'm going to talk a little bit about as a sort of counterpoint is what we would call maybe more broadly energy modeling or performance modeling. And I'll talk a little bit about how we use it within our firm. As we said in the introduction, I was supposed to be a real architect back in the day, but sort of fell backwards into passive house consulting a dozen or so years ago, and that sort of took over our whole practice. So it's pretty much all we do these days is performance consulting for passive house and other high performance buildings. So I'll talk a little bit about how we use various different models within our firm, and then we can sort of discuss how that all interfaces and goes together. So I think it's useful to note or just highlight that, in practice, we use lots of different models for lots of different reasons. And as Mark and Allison already described, it's really important to get those peak load models correct. So we do those for projects, but we might also be doing a lot of parallel models to answer other questions that we might have about the buildings that we're designing. For instance, we might want to understand things like thermal comfort impact of certain material or design choices, or maybe we want to know about the health impacts of mechanical system design, or maybe we want to know about the anticipated energy cost. Maybe we care a lot about how much money we're spending on energy, or maybe we care about energy itself, or, which is a lot of what we're doing nowadays, maybe what we want to know is the carbon dioxide equivalent emissions impact of our energy and material choices. The important thing here to understand is that the models are just tools, and you, the user, has to know exactly what question you're trying to answer. Models only answer very specific questions. They're just tools. You deploy them for specific reasons to answer specific questions. And so all of these different models are just different lenses on the same building. When we take the same building, we might build different models to answer different questions, and we deploy those models intentionally to answer those very specific questions. So let's talk a little bit, though, about energy modeling. Right? For the last few decades, for all sorts of good reasons, we've been really focused on energy and energy cost. So we talk about that for a minute. Now I have no idea what you imagine when we say the words energy model, but all it is at heart, as Mark talked about, is just a recording of all the bits and pieces in the building, more or less detailed, and some of their key performance attributes. And then we use that information to anticipate or predict energy flows in the building: heating in the wintertime, cooling in summertime, domestic hot water all year long, lighting, cooking, appliances, pumps and fans, whatever else. Heat flow through the walls and the windows, the easy part. Predicting how often you and I use the lights and use the cooking, that's the hard part. But there's nothing magic here. It's just a not that glorified accounting of all the bits and pieces of the building. And again, it's just a tool that we deploy to do a specific job. And it's really important to stress that we should know exactly what we want from these models as we're going in before we ever start building them. And we build them in order to answer specific questions. So what are those questions? What are the things we want to know from our models? Well, as Allison pointed out rightly, there's sort of two different niches that these models fulfill. And one of them is on the compliance side. So for all sorts of reasons, for many, many years, we have been asked to build these energy models in order to demonstrate compliance with different codes and programs and standards and whatever else, right? So these types of models are typically done at the end of design, and they're done for compliance. So that's fine. I guess that's useful. These models are done mostly in order to prove to somebody else that you didn't design a big pile of garbage. The more useful role, though, that I think these models can, and in our practice, I think, do fulfill, is that they can be used as design tools. They allow us to try out, to test out a whole series of different what-if scenarios during design. So we can say, well, what if we did this? What if we use this product? What if we use that assembly? What if I do this with the shading? What if I use that? All of those kinds of architectural and engineering decisions can be informed, I think, by this type of modeling. But that means that you have to do the modeling during design. And it means that you don't build a model, you build a whole series of models. And the important thing is to look at the difference, to look at the direction of change, to look at, is this better than that? Does it put me on the right trajectory? So two very different ways that we can use models as compliance tools and as design tools. And of course, we would build them very differently depending on which one that we're working for. So that's useful for doing things like comparing energy impact of like design decisions and products. But of course, that's not the whole story, right? So at the same time that we'll be doing these kind of whole building energy models, we might be doing lots of parallel modeling alongside that. We might zoom in, and as we show here, we might simulate thermal comfort impact of certain design decisions or specification decisions. For instance, here we see radiant temperature asymmetry in a space being driven by surface temperature. It's a function of U value. In particular, at that glazed corner there, you can see the change in radiant surface temperature or radiant temperature asymmetry. This kind of simulation allows us to design in comfort into our buildings from the very get-go, right? It allows us to make design decisions and specification decisions to deliver comfort to the occupants, right? That's our ultimate goal, is to make places, as Marc pointed out, that people love, that they want to use, that they want to be in. And so we can hopefully use some of these tools to try and design better buildings that also, of course, reduce energy at the same time. Of course, where I practice in New York, that wintertime comfort is important, but summertime comfort is just as important, probably maybe even a little bit more important. So at the same time that we're doing those types of simulations, we'll be doing things like shading and solar radiation analysis as part of our modeling efforts in order to identify, overheating risk, to propose better shading for projects. We might be simulating the effect of solar radiation on your skin as you sit inside of a space, inside of a window, and then recommending modifications or changes to locations and sizes of operable windows or other types of strategies in order to improve comfort, reduce energy consumption, and make the building better, perform better, make the occupants happier. So, and all of that is driven by the data or informed by the data. It's not that, it's an important nuance. It's not that we build the diagram, right? But all of these things help us inform our design decisions around how we build our buildings. It doesn't mean we just go build whatever the diagram shows us, but that helps us make choices and informs our decision making. So those are all useful in different ways when we're doing our modeling efforts. We'll probably also, at the same time, though, be zooming in even another step and building any number of detail or constructability models when we're working on projects in order to try and work out things like thermal bridging, airtightness details, assembly sequencing. We use lots of different tools and lots of different medium, all to sort of work on these different aspects of our project and model them in different ways. And again, the important thing here, in my opinion, is that these things are rough. These are working models. These are done quickly during the design phase to help us work out solutions. These are not done as a sort of recording of things we decided using some other mechanism. This is how we design things. This is how we figure things out, is by drawing these things and modeling these things and then trying to make good decisions based on what we learned from the model. Is it always the right decision? No, of course not. But it helps us, I think, make better decisions in many cases. Now, those assembly and detail models are also at the same time almost always going to be analyzed using special simulation software for assessing thermal bridging performance. So lots of different tools that we might use for that, two-dimensional tools, three-dimensional tools. We'll be analyzing things like heat flow, calculating psi values, and carefully assessing things like surface temperatures for mold risk, condensation risk, thermal comfort, and the like. And again, the key aspect here is that this is all done quickly during design, and we use these tools iteratively to inform our design decisions. It's never about a single model. It's about 3 different versions and then seeing which one is better than the other and then iterating and revising and refining on top of those. So again, it's important that we're able to move through all of this really, really quickly and use it during the design phase. So just lastly, and then I'll shut up. I just want to note all the modeling is fun. It's super, it's great. I think we learn a lot from it, but it's no substitute for actually getting on the site. We could have a whole nother session where we talk about how we take that awesome model and turn it into an awesome building. The model is just that. You have to figure out lots of other mechanisms to sort of communicate all of what you learn from these models and get it into, or use that to turn it into a good building. So we do spend a lot of time on site working with folks. Certainly in the world we work in New York City and Brooklyn, we do a lot of retrofits. There's no substitute for being on site and sort of working things out with the construction team. Which just brings me to my very last point, and then again, I promise I will stop and be quiet. I just want to flag one thing here when it comes to this kind of approach that I'm talking about. And this isn't a solution. What I want to do here is highlight an issue or maybe a gap that we see in practice when we work the way I was just describing, when we use these types of modeling and assessment tools during design in a sort of fluid way. There's an issue here where both our clients and the folks who are doing compliance, whether it's the building code folks, whether it's the Pass House certifiers or the living building certifiers, or whoever, choose your green building certification of choice certifiers, there's a gap between the way that they think we are delivering projects and the way we're actually delivering projects. Those folks all think that we go design a project, you engineer it, you price it, you go build it. When in reality, what we're doing, what we find ourselves doing, not on purpose, but sort of what we find ourselves doing more and more often, is we design a little bit, and we engineer a little bit, and we do some simulations, and then we build a little bit, and then we learn a little bit from what we just built, and then we design a little bit more, maybe a little bit differently because of what we just built, and then we engineer a little bit more, and then we do some more simulations, and then that feeds into the building. It's a much more fluid back and forth process, and I think that's good. I think that works well for the architects and the builders and for us. But I do observe that there's a significant gap between that process, that fluid process, and what the compliance folks and maybe even the clients think we're doing when it comes to sort of designing and engineering all of this stuff up front. So again, I don't have a solution for that. I just want to flag that and maybe put it on the table as something that we could discuss. I'd love to hear everybody else's opinions and thoughts on that as well. So that's all I have to say on that. And with that, I'll turn it over to the rest of the folks.
Thank you, Ed. And last, but definitely not least, Mr. Loecher.
Awesome, thank you. I actually didn't have anything prepared, and while I was listening, I pulled a few things together. So let me share that. All right, can you guys see that okay? All right. So, yeah, well, first of all, again, echoing some of Ed's sentiments, it's really great to be here with Marc and Allison and Ed too. I mean, so Ed and I went to grad school together, and we worked on this project that you guys see. And Ed was just a bit above me when we graduated, and I still have learned a lot from Ed as well. So I'm glad to be last year, because quite frankly, I don't have too much more to add to the conversation. So there are kind of just 2 points that I will add, very minor points. And that is kind of what is the value of creating a kind of integrated design energy modeling system, right? So this is directly responding to that last slide that Ed had, where it's like the process is all whacked. Like, how are we going to make energy modeling actually integrated into our design process in an economical way that benefits both us, so we're not pulling our hair out and kind of chasing people around looking for information constantly, but also how can that translate into savings for our clients. The one kind of unique position that I have here, because I'm really not an expert at energy modeling, I picked it up after I got my master's in architecture, trained as an architect, did not have any formal energy modeling experience in my education at all, except for kind of tertiary experience in this Empower House, which was our 2011 solar decathlon entry at Parsons, along with Stevens Institute of Technology. So from that experience, now flash forward about 10 years. In fact, I think 2 days ago was my 10-year grad school anniversary. So I have been teaching for FIAS, the Passive House Institute US, since 2016, and I'm also the building science program manager at Rensselaer Polytechnic Institute. So what I am doing is teaching that base level of energy modeling that I do know to students, and specifically architecture students, to help get them kind of up to speed. So we're not working on this consultant level anymore, where we have the architect, the consultant, this whole level of consultants, but actually we can integrate people right into our design team. Right. So now the work that I do, although I'm still doing mostly consultant work for other architects, I am trying to really integrate that as much as possible, and also empower the students with the tools that they need to do that. I think that's really where we need to go here if we're going to meet some of these climate goals that we're talking about in a really cost optimized way. So the other thing that I did want to add to the conversation was, now kind of picking up on something Mark was saying in the beginning, like what happens when you're not sure about an input, right? So I know personally, when I'm not totally familiar with what an input should look like, or how much energy X device should be actually consuming, I always take a conservative value, right? And that's really a big limitation in the accuracy of our energy models, among other things, of course. There was a lot of different energy modeling programs that we looked at over the past couple slides. One thing that I just did want to bring to the table is this small couple slide case study for a project in Newburgh, New York. It was an existing retrofit project it's currently pre-certified under FIAS Plus 2018 standards. And I think that Whoopee Pro, specifically hydrothermal modeling, including thermal bridge modeling as well, are really the next kind of the next frontier as far as building performance modeling, because it's the tool that we need to unlock in order to really get into retrofits properly, right? So that project that Ben had mentioned that we had worked on, that was a retrofit. The amount of thermal bridge analysis that we had to do on that project to make sure we weren't going to run into uncomfortable positions, mold growth, building durability issues. It's just a necessary part for doing retrofits. And according to the Architecture 2030 projections, by 2035, we're going to have about equal the amount of new construction as retrofit. If we keep going on this current model where we're not really taking on these retrofits so aggressively, we're going to miss out on about 50% of the total square footage that we're actually touching between now and that time. So looking at this project, this was like one of those post-industrial cities, just a total dump of a building. The wall was bowed out, I kid you not, probably about 14 inches in the center. And the builder here still wanted to take it on as kind of a case study, really small project, very manageable, little pet project. So when the builder inherited this building from the city, red guard was applied all over the inside face of that existing CMU. And it ended up becoming quite a problem for us when we were building out this assembly. So we have that existing red guard. The original proposal from this builder is they want to do just a 2x6 wall totally filled with cellulose up until the inside face of that brick. And what we were able to do through the hydrothermal simulation, sorry, it's a little blurry here, is really look at a very, very detailed time lapse. So we're talking about down to the hour here, about how moisture performance is going to be moving through that wall assembly. So, you know, in addition to just taking conservative assumptions, we also have like different timescales that we're working with all of these different energy modeling software. So like Ed was saying, depending on what our kind of intended goal is, we have to choose that properly. And if we don't have an energy model that can kind of look at what we're trying to solve on the proper timestamp, then we kind of have our hands tied behind our backs. Luckily, you know, things like this, WFI Pro, hydrothermal simulation are out there, but they really need to be a lot more readily available because right now there are very few people who can actually master this and integrate it into the design process, like I was referring to earlier. You know, I'm just going to skip through these. You know, long story short, we were able to solve the problem, get the right assembly, free of mold, and ultimately the project is under construction. And we hope to, you know, apply this kind of methodology to more retrofits in the city of Newburgh. That's all I got, guys.
That was great. Thank you, John. Well, this is a tremendously broad and nuanced subject. So just the immediate thing that's in my head is that I totally agree with something that John was saying, that, you know, energy modeling is going to really help us stay out of trouble areas. Usually the time that I'm thinking about turning to energy modeling is when I have head scratcher assemblies where I think that there's a risk, but I'm not sure. So that's where we're turning to energy modeling to sort things out for us. So we have a pile of questions to get through.
Right. And I think related to that, the question that I want to have answered specifically is, should architects do their own energy models or should we be leaving that to engineers and consultants? Specifically, I'm a HERS rater and a passive house consultant, and I do energy models, although I have someone who helps me with some of the more complicated woofy stuff for sure, and working with consultants. And so in my opinion is you should take the courses, know the information, maybe do your base level, but obviously hire consultants to do much more detailed. So I'd love to hear what all of you think as far as clearly we should be doing it, but who should be doing it?
So I'll take a response to that. So I don't think it matters that much, as long as you're not handing off the part where you learn from it and you can spot errors. And the learning from it part is getting to know what a really good output, what a good building does, what it looks like, where you should be doing. The way I think of it, Emily, is where should you spend the next dollar to get the most value? Right? And so it doesn't take too many cycles for you, whether you're working with a consultant or not, to know that going from R40 to R60 in the roof isn't worth a lot if you are still using not so great windows, right? So it's what you're trying to do is learn where the levers are and where the dials are, and understand why some of the dials have limits. So, you know, I'm going to go back to picking on the 12 inches of foam under the basement slab in the passive house. Why did we see those? Well, Germany's a more benign climate than where most passive houses, single family, were built in the early days here. And so you hit up against the 475 like really quickly. And so there are certain dials that you ran out of turning. You ran out of turning. You couldn't get a better ERV than a certain ERV efficiency, and you couldn't get a better window U value than a certain window U value. And you just kept turning the dials that you could turn to hit 475. And finally, you just stuffed EPS underneath the slab, right? And no one said, huh, Like, how many PV panels could you buy for 12 inches of EPS if it was 4 inches instead, right? Because you had to hit 475 and the Germans wouldn't let you account for the PV panel. So it's really getting a familiarity with the consequences of your choices. Ed said it better than I can. It's a tool. And so whether you do it yourself or not isn't important. And I've taught a bunch of architects how to do it. And I always look over those models, and just the very basic stuff's important. So, I'll look at the building and it turns out the building has a footprint of 2,000 square feet and the roof area is 1,500 square feet in the model. And I'll say, are you guys doing the Pantheon here? Like the open thing at the top or what? So garbage in, garbage out. And it's really important to learn what it's teaching you. Whether you're doing it yourself, I think, is really not that critical. But you don't want one model, right? You don't want someone to say, here's the answer. Just like Ed said, here are the parameters. I varied these parameters and this is the consequence. And you're hopefully asking them a question. You're saying, I want to know how much it affects the result if I do this.
Yeah, can I add a little bit to that too? I think that's exactly right, Mark. I mean, I think what we've observed is that there's sort of two things at play. You have to be able to move really fast to do exactly what Mark said. You need to use these models. The way that these models are most useful during design, and so you have to be able to use them quickly during design to answer specific questions. Should I make the wall this? Should I make the wall that? Should I use this window? Should I use that window? Should I do this? Should I do that? You can't wait a week to get a turnaround on that. The other thing that I would say about that, which makes it really tricky, and I say this with love to all of my engineering colleagues, engineers are not always known for their communication skills. So if you outsource a model like this to maybe an amazing engineer, there's no guarantee that you as an architect are actually going to understand what you get back. You might get back exactly the right numbers, but maybe you won't get back all the nuance and all the variables and all the variations that you were hoping. Maybe you won't quite learn. Now, there are some amazing engineers out there who are very good at these things and who are really good at communicating, but the communication is easily as important as the number crunching, right? When we do projects, we spend 50% of our time crunching the numbers and 50% of our time crafting our deliverables, crafting the type of communication documents that we use to communicate what we've learned back to the client. Literally 50 is the way we split up those hours. And so that's really important. So if you're going to outsource these things to somebody else, make sure it's somebody who you can work with, you can talk to, you can have conversations with, who works quickly, who you're able to iterate through. When it comes to compliance work, that's a different thing. Go ahead and outsource that. There's no value in that for the architects. Just choose that over to somebody who does it quickly and fast. If you're doing, 90.1 compliance models or something like that. That's my opinion on that. But yeah, it's a tricky one.
So there's a great detective series where the two characters are Bernie and Chet is a dog, and they're hilarious. And they're narrated by Chet. And Chet says that his job is to catch the perp by the pant leg, but Bernie's job is to take the information in, and then Bernie's job is to do the so therefore. So Bernie does the so therefore, because Chet can only count to 2 as it turned out. And so if the modeler can't say so therefore, then you've lost the effort. And I'm going to recount a short story working on a university building, science building, that was added to an existing large building. And there was this L-shaped atrium. And the architect in-house did a terrific job of a daylighting analysis. This L-shaped atrium had a southwest facade of glass. And because of the heights of the building, it was really difficult because the atrium glass was going to slope the existing building, which is a really shitty situation. That's a technical term for not good. And so she had done this fabulous model. It was really helpful, and no so therefores. So I looked at her model and said, what's great about this is you're showing that we can get rid of the first 6 feet of glass against the existing building and really handle water there instead of creating an insoluble gutter for the next 100 years. But Her model, she didn't report that out to her colleagues. Oh, and it ended up all glass.
Something
So
that kind of
therefore-
something that kind of popped into my head as we were discussing some of this is, I think in some ways these models are quantifying what previously would have been career wisdom gained by a knowledgeable contractor. They're giving us ways to, you know, those old, like the rules of thumbs or the anecdotal experiences that contractors get over decades working in the fields. Now we can generate a model to kind of give us a picture and clue some of us who aren't as smart into what's actually happening with our buildings so that we're making informed choices.
I think in a way though, Ben, it actually opens up even more than that, unless you're like a traveling contractor and you've worked all over the country or all over the world, because, you know, one of the, I think, most beneficial exercises when I'm teaching students, whether it's professional or collegiate, is to, okay, now change the climate data. And what does that do to your model? How is your model, your results now different? And then what would you start doing to troubleshoot that? Because, you know, if you look at, you know, beyond just temperature differences throughout the United States, we're looking at, you know, solar radiation differences. We're looking at different geothermal opportunities, wind opportunities, like the list goes on. It's a very, very nuanced differences in, you know, all different parts of where we might be conducting our work. So in a way, you know, these energy models and our climate data really allow us to open up. And actually what that really does is more than anything reveal how necessary it is for us to vet our climate data and understand that what we're putting in there, that starts everything for our model.
So in that same line, that brings up another question that popped up during the talk. So Mark, you showed some information where you were comparing what looked like actual monitored performance data from projects versus the model during design phase data you had. How much are you guys collecting data post-construction to help verify what's modeling?
Well, I'm an obsessive post-construction data collector at all scales of my buildings, and that informs the next building. And I think that's why we're seeing in large buildings in particular, we're seeing sets oversized systems, because I really think that the engineering profession is very lax in looking at what the performance of the building is that they designed. It's really, because to some extent the architect should be doing that too, but the engineers seem to be less interested in it as a gross generalization. And it's and you know, I think people know this, at least in large firms. Engineering firms are much more profitable than architecture firms in general, and it's because they don't spend any extra time. That's why it's been hard in, you know, like the lead world to get that upfront input from the engineers before the building is pretty much designed. You know, when Ed talks about testing all this stuff, who's testing it? It isn't the engineer, unless you've got a pretty unusual engineer, because they're taught within the firms, don't do anything more than necessary in schematic design, because that's where you piss away a lot of money as the architect keeps changing the plan. And I am not exaggerating. So Ed is smiling, and maybe he's encountered this. I'm old, so I've encountered it over and over again. And so you've got to measure what you did and look at it and talk to people. Like, and you should go, I'll tell you, one of the greatest things to do is, again, I don't think this is so much a residential case, but I like to go to buildings that I've designed at 1 or 2 in the morning. Like, what's going on? What's running that shouldn't run? You know, that kind of thing. It's really, really interesting to look at what happens when you're not in the occupied hours and what's going on in the building.
Do you put that in your contract, Mark? I'm allowed to come to your house anytime I want to.
No, because it isn't really a house thing. You know, it's really, it's a big building thing. And if you look at this data, you can find, you can see, so that I mentioned the MIT School of Management. It's like a 220,000 square foot building. We set really tight limits for peak loads and not so much annual energy consumption, because we thought if we really get these peak loads down, then the energy consumption efficiency will result. And so we set 1,000 square feet per ton. So Allison, I'm not sure how that, you'd have to, move your graph a little bit to get there. 1,000 square feet per ton for a big institutional building is a very low cooling load. And after a couple of years, that building was peaked at 1,100 square feet per ton. It actually beat that very tough number. But the energy use was higher than I expected. It really was higher than I expected. And the facilities people there are really good. And they said, this building isn't doing as well as we thought. So I said, well, get me some detailed output. And I really looked at it and I said, you know what, something big is running all the time here. And I think we need to look in the kitchen. So it's got a big commercial kitchen in it, a big food service thing. So what do we use when we do something like that? We use variable speed range hoods, right? Because we want them to only run when they really need to run hard. And what do they sense to control the variable speed blower? They sense the opacity of the exhaust stream. Is it smoky? Well, commercial range hoods have fire suppression. And I can tell you that if you put a pipe in the electric eye that is sensing opacity, if the pipe runs through the electric eye for the fire suppression system, the range hood will think it's running, it has to run on high speed all the time because it thinks it's smoky all the time. And the director of facilities engineering thought that was 30% an adder to the energy use of that building. 30%. Because they put the fire suppression piping in the sensor beam for the range hood opacity. How would you know that if you're not looking at some kind of data?
I've seen some strong range hoods, but never one strong enough to suck a pipe out of a building.
This is a totally different conversation on coordination drawings too, which never happened in residential, right? Like these two things going, although the eyeball probably wouldn't even have gotten caught on those. But I think we need a whole nother BS and beer show just on verification, right? And crowdsourcing information. It's like you built this energy model, you used it to inform the decisions you made, and then you never check if it does anything afterwards. Like, that's great. But what I keep seeing it popping up in the chat repeatedly, but there are some people who are new to getting into energy modeling and who want to know specifically about some of the outputs that you shared in your slides. What's everybody using? And if you're new to it, where do you start? Because some of the, as you mentioned, the passive house softwares or the thermal bridging softwares are hard to get right. And so where does somebody new to energy modeling start for, I guess, either load calculations or performance modeling?
I would say home energy ratings are a good introduction to energy modeling. Ben took, we used to teach HERS class at Energy Vanguard, and Ben took our class a few years ago. On the load calculation side, there are free tools online that actually do a decent job now. CoolCalc is one of them, and you can go online and play around with that. And if you have a house, you can model your house and see how it compares to what the load calculation is, and then play with the load calculation until you get it right. That's a great way to learn.
I do think that it's really to emphasize something that Ed said. The tools need to be agile. You've got to be able to use them quick and fast. And in the courses that I teach on zero energy houses online, all those calculators are just Excel based, and they don't have the detail that PHPP or Wi-Fi passive has, where you're describing each window and how much it's inset from the outside wall, and that's too detailed. You can't do it fast enough. And if the house is fairly simple, I can build that model in an hour. and then I can run 20 cases in the next hour because it's all right there in front of you. It's Excel. And the black box models, what were people picking in the manual J that gave them an extra 60,000 BTUs an hour of infiltration in the examples I gave? And what were their choices? Tight, sort of tight, not so tight, leaky, and oh my God, I can see outdoors everywhere I look. That's not a fine enough set of choices. Typically, we're setting an air tightness target. Most of the people who are probably on this call are setting an air tightness target. And how does the software relate to that air tightness target and model the infiltration accurately? And I think, I don't know what Woofy Passive does, but I think PHPP pretty much, for house size buildings, was taking the blower door number and dividing it by 5 roughly. And basically I looked at that and I thought, and I did a bunch of math and I said, that's kind of what I've been doing too. So is that the right number? Should it be 5.4? In one of Ed's slides, the temperature inside was 20.0000. And I was appreciative of that because I knew it wasn't 0001.
Yeah, that's a good point. What was the question? Oh, on the software side, I want to just echo what Mark was saying about transparency. I mean, I think whatever tool you're using, to me, one of the most important things is that the tool is transparent and that you can understand what's happening. I have to admit, I am not at all a fan of these powerful but opaque tools out there. And unfortunately, a lot of the simplified tools that you might find that are designed to be easy to use for new folks, they obscure too many things, and I find that incredibly difficult to understand what's happening. And I think as a new practitioner in particular, you'll find it really hard to understand what's going on. Things will change and you won't know why or how it happened. I'm a big fan, a big proponent of transparency in all things, but especially in models. So I would use whatever. I mean, all of these tools can work, but I would prize and prioritize things like transparency in whatever tool you choose to use, whatever tool you want to use. Yeah, I guess I'll just leave it at that.
Yeah, sorry to pick up there, but I think also part of it comes down to what is your intention from this? Are you just trying to educate yourself and kind of raise the bar and kind of get your feet wet? That's one situation. Mike Main's put in the chat that he uses BOPT from NREL, which is a free program and works quite well. Years ago, I took Allison's ResNet course and learned how to do REM rate, and then branched off and learned how to use RightSoft to compare heat loads for my mechanical contractors and find out whether or not they were even doing them. So it really kind of comes down to what you want out of it. Yeah. It seems like every time I turn around, Allison mentions CoolCalc. Every time I turn around, there's another tool out there. I'd say pick any of them and just start playing with them.
Yeah. It depends on what you want to learn, right? It depends on what question you're asking, what you should use. Yeah.
Right. And again, it's also about what your process is. So, if right now the energy modeling tools that we're talking about are largely divorced from the design tools that architects are using, right? So we build a model. Every single time I work with someone as a consultant, they say, hey, I already created a Revit model or whatever, can you use that? No, sorry, I have to start from scratch. So is there a way to start to bring these things together? And there are some really interesting kind of, on the new end, energy models that are plugins for, Rhinoceros, which, like architecture students are using for design all the time. And you can run scripts in it. And essentially, there's one piece of software that I've been teaching at RPI for the past year called Climate Studio. It uses Energy Plus, the Energy Plus as a whole building energy, simulation, but it can also do like daylighting analysis. And it can be just like integrated with the same model that students are using for their drawings and for their renderings. So, I think, of course, that's going to be limited. It's not going to be anything like what, PHPP, Woofy can do and sort of the amount of, inputs is a very small fraction of that. But I think we do need to move towards something like that. So again, we can get these things more integrated into an architecture practice or a design practice for maybe just the basic projects, right? And then you can leave the non-residential projects or the larger multifamily projects to a consultant, right? So that's kind of another way to get into it is take on a project when the kind of risk is low. Like right now, if you were to design a passive house and use Woofy or PHPP, there's so many people you could reach out to now to say, hey, like, do you mind just taking a look at this model really quick? Like, we need people to do that because there's not enough of us that can just like focus on energy modeling and load calcs all the time in order to actually make the kind of massive changes in the built environment that we need to do right now.
Let me throw a little bit of a different perspective in there. A lot of people here are talking about keeping things simple and having everything be transparent. But here is what Manual J looks like. Manual J is a very thick book. And if you're doing load calculations according or energy modeling according to some protocol, there are all kinds of inputs that have to go in that. And yeah, I agree with Einstein, who said everything should be as simple as possible, but not simpler. So sometimes you have to have that complexity, and it pays to have somebody who has a lot of experience with these kind of calculations and the software used or spreadsheets or whatever, because there are a whole lot of inputs that go into modeling a whole building, and it's easy to overlook things because there are so many things to overlook.
I think, can I pick up on that? I'm glad you brought that up, Allison. I noticed Greg had noted something about that too, about complexity. I had wanted to include something about complexity in my slides, but I couldn't figure out how to broach it. I think that's such an important topic. Like, I think it's really important for us to recognize that, like, as an industry in the energy modeling world, like, we've done a horrible thing with a lot of these tools and protocols that we've developed. I just came up for air after like a 6 weeks long ASHRAE 90.1 section 11 model for a 500,000 square foot building. And like, what a horrible thing that we've done by creating that protocol. Like, what an awful, complicated, Byzantine, ridiculous mess that document is. It's just awful what has evolved. And God bless all the people who made it. They all were trying their best, but it's just, these things have accreted over decades or over years. And we've never gone back and swept up and like cleaned up a lot of these protocols and documents and tools. And it's really an important subject, especially if we want more people to do these things, if we want more folks to engage in these things, we have to really somehow radically simplify and maintain transparency and accuracy in both our tools, but also in our protocols, also in our like rules documents. Again, God bless, I love, we do PHI and PHI US and ASHRAE stuff all the time. I love all the people who do all that stuff, but like 300-page manuals and section 11 and appendix G, why can't they both be sections? Why couldn't, maybe they could both be appendixes? Why is one in the other? These kinds of things
or
really build up over time.
Why couldn't it be a pancreas? Why is it always an appendix?
Exactly.
Don't forget spleens, Mark. There's spleens in the world too.
That's right. Good point. I totally, and like I said, I've looked at a lot of big energy models on big buildings, and some of them are just fantasy. The outputs are fantasy. These lead models are fantasy. And I got a call, I don't know, 8-9 years ago. Could you review an energy model for us? Sure, I do that all the time. And I go into it a little bit, and it's a science building. Okay, yeah, I can do that. And then I realized that they're talking about a building that's built. And so what's the problem? Well, it's using 4 to 5 times as much energy as the model. And it's a LEED platinum, right? It's, of course, it's got to be a LEED platinum building, right? It's a LEED platinum building because you get the plaque before you have to show how much energy your building used. And I said, so wait a minute, why are you asking me to review the energy model now? The building's built. Well, they were lawyers. I don't want to work with lawyers. I mean, God forbid. I said, so, I'm really interested if you want someone to help you figure out how to reduce the energy use of that building and what's going on. But if you're just looking to be fighting about who made what dumb error, then, you know, find someone else to do that, because that's not fun after the fact. But that's the level of what some of these models are giving for output. And
Well,
if
you know what?
don't know what the answer should be, what, you know.
Yeah, but I mean, I think it's a good point though, Mark. But I think also as we move forward into like whatever this new universe is going to be, where we're going to have more stringent compliance requirements around things like energy or carbon, whatever it's going to be, however things are going to evolve over the next 20 years, it's hard to imagine a scenario where things become less risky or less litigious, or where people are held less to account for the performance of their buildings. And so I think those types of issues are things that we're going to have to somehow learn how to wrestle with, I guess, because I can't imagine a scenario where less folks are going to pay attention to those kind of things moving forward, I would imagine.
Yeah, so there was another question that came up kind of related to that, which is with the amount of assumptions and averages that we code into it, at what point are we overcomplicating or overthinking what our calculations are doing? Like, where's the break point?
I mean, yeah, it's a hard thing to say. I mean, I guess what I would say is that the tools that we like the best are the tools that allow us to modify whatever we want. So like if we want to get as complicated as we want, we can go in and edit any of those things and adjust any of those variables. But that out of the box, they include a bunch of like reasonable, rational defaults and sort of simplifications. So they're like both easy to use and get started, but then as you want to modify them and as you want to add detail to them, you can start to do that. But I 100% agree. You don't want any tool that forces you to do everything perfectly to the nth degree, Energy Plus, I'm looking at you, all the way and get every single period in the right place. Otherwise the whole thing blows up and explodes. And like you get nothing, you get a zero and a list of errors, right? Like that's not a tool that you want to use. You want to use some tool that's forgiving and allows you to like refine and get more detailed over time, I think, personally, at least.
Yeah, exactly. And I think it's about knowing, you know, what quality of information you can use at what stage in the design process. Maybe if you're, you know, just trying to get some overall views about, you know, R values in an assembly or something like that, maybe you don't need to, you know, do a therm analysis of all your, you know, window install details at that point. You can just use some placeholders. And that's reasonable. But actually, if you did those thermal bridge analyses, you'd see likely, you know, your SI install is either much better or much worse than that placeholder. And that's really where you want to be towards the end of the project, or as close to that as possible.
For me, the energy modeling experience that I have, and it's fairly minimal, was a way for me in pre-construction to be able to just grossly turn the dials to figure out what's the most cost-effective building I can deliver for my client. And it's really just very broad stuff like, do we do 1.5 inches of polyiso on the outside, or do we do 2 inches of polyiso on the outside? If we do 2, does it drop the heating load on the place so that we can go to a smaller unit and save $600 to pay for the polyiso? You know, it's not this in-depth, you know, therm modeling like you're showing. Projects that I work on now, we go to that depth, but that's a whole different thing. For the, you know, the vast majority of contractors and designers out there, we're just looking for broad brush strokes to figure out what our buildings are doing so we can make informed decisions.
And instead of those broad brushstrokes, what happens is this another, or how much confidence do you guys have in alternative wall systems, right? So like Adobe, Cobb, Randerth, Hempcrete, like when you start getting into the really, I don't want to say obscure, less normal things, or well, whatever's normal,
Less
but
typical.
people, less typical.
Like
there you
the
go. Thanks.
obscure things.
Like the obscure things. Yeah. Like,
spleens.
It's like spleens and you know, some other random part. So are there models that account for this, like as we're starting to look at kind of alternative methods to that? Is there any confidence in existing?
So I don't know enough about Woofy because I don't run Woofy passive, but back in the old days, when computers ran on things called DOS, there was a model that was written by two of the most brilliant humans that have ever been in our building field. At least one of them is no longer with us, Larry Palmiter, and Terry Wheeling wrote Sun Code. And it was first called Sun, I don't know, it was Seri Res, that's what it was. And it was a network, thermal network program. Talk about transparent, Ed. I mean, you know, it told you everything, but there weren't defaults, right? So it wasn't drop downs. It was like you had to write it. It didn't take a huge amount of time. What it did take is you had to know what you were doing. So Emily, the interesting thing about that program is you could model a wall as a pure thermal resistance, which is kind of what our simple softwares do. And you could put some thermal mass in it. And it was what some of us, like old people like Drew Gillett probably remembers this, brick in a box, right? Brick in a styrofoam box. But then as much as you wanted to, you could take that wall and put capacitance in it. You could layer it. So this first layer is an inch of stucco plaster, and then the next inch is this, and you could have as many nodes as you want. And you're giving each one of those layers a thermal resistance and essentially a thermal diffusivity and a mass. So you'd have to know what things like thermal diffusivity are. You know, that makes it a little more difficult, but it wasn't anything complicated, completely transparent. And so you could start with a brick in a box model, and then you could say, okay, so this layer has this kind of thermal storage in it, and this surface gets direct sun, and this surface doesn't, which makes a big difference with thermal mass. And so you could go through it and basically tune the model, and the model keeps getting more finally, you know, the more gradations, and you could actually tune your building. It's when people cared more about heating and cared more about passive solar, and it was an amazing tool, and it doesn't exist. It got ported into an early Windows program, and it was called Sunrel, but it was never supported. But I'm imagining that the more sophisticated WFI tools will allow you to do that, and layer, and even if it was a wall that was monolithic, like if it was a trom wall or a cob wall, you could still decide to treat it as one node or 10 nodes, and then when you had 10 nodes, you'd see the temperature profile across the wall change over time. And to Ed saying about things blowing up, it took all night to run a sophisticated model back then, right? And then in the morning, it's like, oh shit, you know, you made some stupid error and you got garbage, you got something out, but it was wrong, and you could tell it was wrong. So, you know, I want that piece of software that was so transparent. All the network equations were written in the back of the manual, and the manual was like this. It wasn't like it was like this. So yes, you can model those cob buildings, and you know those tools have been known for decades, but they're not easily accessible, I think, to most of us.
Can I add something to that? Unless John or Allison, you guys said. I think that's probably right, Emily. I think there probably is a lot of utility in you. Like I said, you use these models to answer questions. So you come upon a new thing you've never seen before. That's when these models are most useful. Except the qualifier there, and I think it was Robert Bean, the engineer from Canada, who I think I remember him saying something like, "When you're using the computer is just a tool to speed things up. You should already know what kind of answer you're going to get." So the qualifier there is you always have to temper your sort of use of the computer, the tool, because you can get all sorts of wacky numbers out of these things. So especially when you're using these tools on assemblies you've never built before, materials you've never worked with before, you have to go, I think you should go in with a lot of skepticism and be really cautious making decisions about things you've never touched, used, worked with, based just on the numbers you get from the computer, because the computer can give you all sorts of ridiculous numbers. So just to add that as a qualifier, like, yeah, they can be super useful when you come upon new situations, new climates, new areas you've never worked in before, new assemblies, but you got to be really careful as well.
You test it with something that you know the answer to, Ed. Right? You test it first and you say, well, I know this is the answer. And if you don't get the answer that you know is right, then you have to figure out why the tool isn't giving you the right answer. At least that's a first, I think that's a first step. And then the other thing you do is you test the endpoints, so you crank something all the way to one end and the other. And do you get ridiculous answers, or do you get answers that you believe?
We have answered I don't know, 2 questions that popped up in the chat. So
there's a solid 30 more.
there's so many more questions. I don't even know where to start with 4 minutes left in the show. So actually, since there are 4 of you, I think the reality here is I get to be the chopping block that ends it. But I'd love to hear each of your kind of final thoughts on energy models or load calculations or both. Kind of what's the takeaway? Why aren't we doing it? Why should we be doing it? What should we be doing? I don't even know what questions to ask here.
When should we be doing one or the other?
Right. So, each of you can kind of answer that. So we'll go in presentation order. So I don't have to think about it. So that makes you up first. Mark, you went first, didn't you?
I think people should be picking a tool or a modeler for either load or energy, and then looking at results. So, for instance, if you've got a load calculation program and someone's used it and you've got a building you like, throw a data logger on that heat pump or boiler or whatever. And on the coldest night of the year, how many minutes did it run? Right? And that tells you what the real load of the building is. We recently did that for a bunch of city buildings in Western Mass. And they're using less than half of the calculated loads. Old buildings. Old crappy buildings.
So true. Allison?
Yeah. So we covered some good points here tonight, and I'd like to close by saying that the modeling is important, and on the load calculation side, we didn't spend a lot of time talking about that, but the load calculation is not just for sizing the system. That is an important part of it, but it's also for getting the loads for each individual room so you can get the distribution right, because you don't want to get the whole house system right and then send all the heat into the living room and everybody's freezing in the rest of the house. You got to get that part right too. The other thing I wanted to say to close is you've got to have a feel for what's real in your load. So, I started off talking about 500 square feet per ton, but if I do a load calculation, or somebody at my company does a load calculation, and they come out with a load that's 500 square feet per ton, I'm going to say, no, that's probably not right, because we don't do those kind of houses. New houses now are almost always over 1,000 square feet per ton. I say almost always because sometimes these people in Florida want to do single pane windows and have a whole wall full of windows facing south or west or something crazy. But when you get a feel for it, you can bracket it like Mark was talking about. You have an idea of, look at the house and say, okay, this is probably a 1,500 square feet per ton house. You look at a house with a basement, it's maybe 2,500 square feet per ton, depending on the air tightness and things like that. So have a feel for what's real. And if you can do stuff with your own house or monitor data in other houses that you've modeled, that's a great thing too. I have designed the system in my house. I've monitored it. The system in my house, the cooling system, it's a Mitsubishi multi-split, 2 SEZ air handlers. I sized it at 88% of the load. And last summer, it did just fine. It dropped off the set point just a little bit on the design days, but not much. So it was pretty good.
That's too funny because I swear I say it all the time to people. Like, you don't want to come to the architect's house and see it, or the builder's house, or clearly the engineer's house either, because that's where we test everything. Our own houses to see what works. So the verification data we're all doing at home. Ed?
Yeah, okay. Wrap up. Well, I guess I would just say that these are really powerful tools. It's a fascinating universe to work in. I enjoy it a lot. I like working with our clients. It's a lot of fun. And I think we're bringing a lot of value to projects. I hope we have a lot of clients come back over and over and over and over again. So I suppose that's a good sign. They seem to get something out of it. So I would definitely encourage anyone in the audience to start educating yourself on these software packages and tools. These are really powerful tools, and they're really useful things to have in your tool belt, for sure. But approach them with some skepticism. Be cautious about how you deploy them, and be thoughtful about how you use them. But then, just to reiterate again over and over, they're just tools. You use them for specific purposes to answer specific questions. And so you have to bring your own questions. Do you care about cost? Do you care about energy? Do you care about CO2? Do you care about peak loads and distribution? You have to bring your own values to the table and say what you care about before you ever pick up and start to use these tools. So just to repeat that over and over and over again, just because I know we see a lot of, especially new practitioners, who get lost in the buttons and the numbers. So just try and remember that. I know it's hard, but try and remember that as you start diving into these tools. We'll leave it there.
Yeah. John?
Sure. I think in my experience, kind of being in this field, like, again, just coming from the path of an architect into a passive house consultant, I found that it's like a very kind of muddy waters, like it just a high performance, building in general, like it's somewhere in between architectural design. It's beautiful, but it's also engineered. And, where exactly do we all fall into, and I think there's a lot of opportunities, and having these conversations are really great because they help kind of make that a little bit more clear. Like what I'm kind of feeling inspired now to make like a flow path. Like, what is your question? And then like, which piece of software do you go to, to just, efficiently solve that? That would be like, really, really wonderful. And hopefully we can all just continue to contribute to that.
I think if you made that page as a link, you would find that was a super popular, because I feel like I get asked at least once a day, like what certifications, training have I taken? What software do I use? Because I think it's awesome people are asking these questions, right? Because however, not that many years ago, not enough people were asking those questions. So it's pretty exciting to me. This is my world. We could have geeked out on this for a whole lot longer. So thank you guys all for sharing your vast knowledge. Like we said, there were like 30 more questions. So if any of you tune in to the Green Building Advisor blog afterwards that Kylie will put up, there will probably be a whole lot more questions for you there. So thank you.
My one takeaway this evening is, why use a little word when a big word will do the job, and it can be billable by the syllable.
Yeah, I think Mark won that. Billable by the syllable.
Thank you, everybody. Phenomenal talk.
Great having you.
Thanks, guys.
Thanks, everybody.